Okay, so now the topic is still about density estimation, but on a completely different space. And this work has been achieved with the help of Ivar Farup from the University of Gjøvik in Norway. I will start by formalizing the notion of image histogram in image processing, which is slightly different from the notion of histograms in statistics. I will then briefly present the macadam ellipses and the perceptual metric on the space of colors. And I will then talk about density estimation on the space of color under the perceptual metric. So first, we can see an image as a function I going from a support space omega to a value space V. And omega and V are endowed with measures which usually reflects the geometry we are using on omega and V. So usually omega is a square or a parallelepiped, and the distances on the support space are usually Euclidean. Then the measure we're using on omega is usually a restriction of the Lebesgue measure. So the measure on omega can be transported on the value space with the application I. And now what we call image histogram is any kind of estimation of the density of the transported measure with respect to the reference measure on the value space. So actually an histogram can be kernel density estimation. So now the image I is known on a finite set of pixels, and usually the pixels are uniformly distributed on the support omega, and uniformly means with respect to the measure mu omega. And it means that we can consider the set of I of P being a pixel, as a set of independent draws of a random variable, and then continue as if it was a problem of probability density estimation. So now we will assume that the value space is now the space of colors, endowed with the perceptual metric. So perceptual means the distance perceived by our brain. And we will assume that this metric is Riemannian. And this was actually one of the first examples of a Riemannian manifold gave by Riemann himself. And so the volume measure we're using on the value space is the volume measure induced by the Riemannian metric. So the macadam ellipses are sets of just noticeable differences. So it means that inside macadam ellipse, it's not possible to differentiate two colors. So macadam made many measurements to build 25 of these ellipses in a space of constant luminance. And these ellipses, they can be considered as elementary balls of the perceptual metric. So here we have an information on the local scalar products of the Riemannian metric. So there are various perceptual spaces. The most famous is the LAB space. And in this space, the Euclidean distances and parameters are supposed to match the perceptual distances. But when we transport the macadam ellipses in the LAB parameters, we can see that these ellipses are far from being balls. So the Euclidean distance on the LAB space is far from perfect. So densities are a local densities. It's a local notion. It normally does not involve long geodesics, or so. If in your density estimation you only have to deal with small distances, which is the case when you have a lot of data, then the information on the local scalar product should be enough. And in that case, you don't need a globally perfect perceptual space, or you don't need the knowledge of very long geodesics. So from now on, dr will refer to the perceptual metric, and double bar LAB will refer to the canonical Euclidean metric on the LAB space, and double bar C will refer to the Euclidean metric induced by a given ellipse. So around a point C, the distance induced by C has every chances to be better than the canonical distance on the parameter of the LAB space. So first, this is a standard Euclidean kernel density estimator using the LAB distance, and we could be tempted to replace what's inside the kernel by a local distance when the distance between x and I of pi is small. And this assumes, of course, that the ellipses have been interpolated to have some scalar product in any point of the space. So it can be shown, it's a bit technical, I will maybe not enter in the details, but when you get closer to C, you can show that at some point it's better to use the local distance than the LAB distance, unless they are identical in C. But so since if we're using kernels with bounded supports, so we are sure that for sufficiently small kernel, we have to replace, or I mean, it's better to replace what's inside, I mean, to switch from the LAB distance to the local distance. So I maybe can provide more details after. So I was talking before about the interpolation problem. So usually when we interpolate a function, we try to minimize its variation with respect to a metric. The problem now is that we want to interpolate these ellipses, but the ellipses define the metric. So we try to interpolate a metric. And then it cannot be achieved in an intrinsic way. It has to be done with respect to a parametrization. So we didn't push the study very far in this work, and it will be the subject of further study, but we choose a very simple solution, which consists in interpolating the parameter of the ellipses in the LAB space using a barycentric interpolation. So here on the top left, you have the ellipses in an AB plane. Top right, you have a triangulation of the center of the ellipses. Bottom left, you have the interpolated ellipses. And bottom right, you have the map of the Riemannian volume measure with respect to the Lebesgue volume measure of the AB parametrization. And the maximum of this map is around colors of low saturation. So now just a small example, I took a color photography, And here I just rescaled the Riemannian volume measure to the colors present in the image. And now to conclude, I computed 3 different histograms of the previous photography. So the histogram on the left is a standard kernel density estimation on the AB plane. The histogram in the middle is just the histogram on the left divided by the volume change. So now it's an histogram, it's a density with respect to the Riemannian measure, but computed with the LAB kernels. And on the right, I used in the kernels, I replaced the LAB distance by the local distance. So we can see that the top peak decreased against the Riemannian volume measure, so the histograms are different. And we can also see the influence of the choice of the kernel when we compare the middle and the right histograms, where we can see the shapes of the ellipses appearing more clearly. So to conclude, so this observation on ellipses is a simple observation which enables me to be more faithful to the Riemannian metric without adding additional computational cost. And our future work will focus on the question of interpolation of the ellipses. So to really understand what does it depend on, is there a better set of parameters to interpolate the ellipses? And also on the construction of longer geodesic in the Riemannian perceptual metric, because density estimation do not rely on long geodesic, but many different applications in image processing do, like averaging. Okay. Thank you for your attention.